So let's begin with some basic definitions of probability. Now we should know that probability yes. Okay, let's begin. So first we begin with basic definitions. See, probability is a science which talks about the chance of occurring of events. What is the chance? It is a estimation of an uncertain event, um, that what is the likelihood of an uncertain event to occur. So like based on weather predictions, that tomorrow it is likely to rain. So what is the probability that it will rain in the morning hours tomorrow? So there are certain methods to calculate that and make that prediction. So, and we say that there is say 50% chance that the rain is likely to occur tomorrow. So that 50% is the calculation of probability. So it is 50% probable that tomorrow rain will occur. So now to understand, to develop that kind of a probability theory, first we should understand the basics of a probability theory. So the very first definition is that of random experiment. So a random experiment is an experiment whose all possible outcomes are known in advance, but the outcome of any specific performance cannot be predicted with certainty. So that is a random experiment. So for example, rolling of a 6-face die. So we know the dice that we use. Dice is a plural, die is a singular. So 6-face die, when you roll, the outcomes are, say the possible outcomes are known. So possible outcomes are either 1, 2, 3, 4, 5, or 6 will occur. Of course, in a die, these are shown as dots, but these are for count, there are 6, 1 to 6 numbers. Now, the question is, now when I roll a die once, do I know what number will turn up? So I cannot tell for sure that a particular number will turn up. So we say, so a specific performance cannot be predicted with certainty. So that is what it is. A specific performance cannot be predicted with certainty. I cannot say that now I'll roll a die and I'll get the number 4. I cannot be certain about it. So we know all the possible outcomes, and on a particular experiment, on a particular performance of the experiment, we don't know what outcome will come of all the possibilities. Such an experiment is called as the random experiment. So this is example 1. Example 2. Tossing of a coin. This is easy. There are possible outcomes are heads or tails. Heads or tails, and then any one result can occur, either heads or tails, and we cannot predict it with certainty. So this is called as the random experiment. So this is the first definition of the random experiment. Next is the definition of sample space. First, before going into all, first we will define sample space. So sample space is the set of all possible outcomes of a random experiment. So yeah, so we can denote, so because it's a set S. So again, example 1, the same example, rolling a 6-face die. I'll just try rolling of a die. Now the sample space, okay, S is 1, 2, 3, 4, 5, 6. Set of all the possible outcomes of the random experiment is called as the sample space. And each outcome is called as the sample point. So these are the sample points. Now I will change to rolling of 2 dice. So when I roll 2 dice, then the sample space there are 2 outcomes now. The first die can give me a 1, but the second die can give a 1 or a 2 or a 3 or a 4 or a 5 or a 6. So we get 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, and 1, 6. Okay. Now, the first die can give me a 2, but the second can give again 1, 2, 3, 4, 5, 6. 2, 1, 2, 2, 2, 3, 2, 4, 2, 5, 2, 6. Similarly, the first die can give me 3, second 1, first 3, second 2, and then we have 3, 6. Similarly, we'll get 4, 1, 4, 2, 4, 6. Then we have 5, 1, 5, 2, 5, 6, and then lastly 6, 1, 6, 2, 6, 6. So this is the sample space. Same rolling of 2 die, but all the possible outcomes when we put it in one set, so that becomes the sample space, and each of the outcome, say 3, 2, is called as the sample point. Okay, another smaller example, tossing of 2 coins. Tossing of 2 coins with heads and tails. So what will be the sample space? Anybody? what will be the sample space? First coin can give a heads, second can give heads. First coin can give heads, second can give tails, or the first coin will give me tails, second heads, then first tails, second tails. So there are four. So these are called as, the sample space and sample point. Now depends on the random experiment. The first random experiment is rolling off a single die. The second random experiment is rolling off two dice. The third random experiment is tossing off two coins. For each of them, we get a separate sample space, all possible outcomes. Okay, if you're not understanding at any point, please stop me and ask. So once we have an idea of what is a sample space, now there are different kinds of sample space. So the first one is finite sample space. So a sample space containing a finite number of points that are countable. That is called as a finite sample space. So this is an example of finite sample space because the number of possible outcomes here are 6. So it's a finite sample space. You can count it. Here for the second experiment, rolling of two dice, this sample space is also a finite sample space because the number of outcomes or the size of the sample space is 36. 6 into 6, 36. So the third experiment, the size of the sample space is 4. So you can count the number of sample points. So sample space contains finite number of points that are countable. So that is finite sample space. Sometimes the sample space is called as the countably infinite sample space. Countably infinite. For example, a sample space is the set of natural numbers. Randomly, you choose any natural number. Now, set of natural numbers are infinite. So sample space containing infinite number of points that are countable. So example, set of natural numbers. I can count them 1, 2, 3, 4, 5, 6, but they are infinite in numbers. So we say countably infinite. Then there is another one, non-countably infinite sample space. Non-countably infinite means between one point and the next point, it is very difficult to find. What is the point? So a sample space containing infinite number of points that cannot be counted easily. So example here is set of all values of x such that x belongs to open interval 0, 1. And we should add, I will add this. This is not sufficient. X belongs to natural numbers. Sorry, x belongs to real numbers. And x belongs to the interval 0 to 1. So x takes all real values between 0 and 1. Now, how many such points exist? This is 0. This is 1. Now, there are infinite number of points between 0 and 1. So, although it is a small interval, 0 and 1, open interval, that too. Yeah, you can mark this as an open interval. Now, between these, all these points in between, there are infinite number of points, and you cannot count this. Can you say after 0.15, what is the next number? If I say 0.16, it is wrong, because between 0.15 and 0.16, there are infinite number of numbers. So you may say, okay, it is not 0.16, it is 0.15001. Okay. No, because I can find another number which is much lesser. Let's say like this. So there are infinite number of numbers. So you cannot count between one point and the next point. Such are called as non-countably infinite sample space. The other way to classify the sample space. So this is one classification. Finite sample space and infinite sample space. In infinite, they are countably infinite and non-countably infinite. But more often, this is used to understand sample space. We call this as the discrete sample space and continuous sample space. This non-discrete or continuous sample space. So a sample space which is finite or countably infinite is called a discrete sample space. So example, all these sample space are discrete because I can distinguish between one outcome and another. So 1, 2, 3, 4, 5, 6, I can count it and I can distinguish between the outcomes. So that such sample spaces are called as discrete. So a sample space which is which is finite or countably infinite. So example, sample space of set of natural numbers. It is also discrete. Discrete in the sense you can make a demarcation between the outcomes. So you have 2, 3, 1, 2, 3, 4, 5, 6, 7, 8. You can count or distinguish between the different outcomes. Whereas here, this is non-countably infinite sample space here, 0 to 1. Now this takes all values between all real values between 0 and 1. Now we cannot count it. So we call non-countably infinite. However, the other way to look at it, it is continuous. There are no breaks. It is not that only integer values or only natural numbers. Continuously on the real number line, all the points are contained within the sample space. So such a sample space is called as the continuous sample space. Okay. Now these are very fundamental definitions because we will keep going through this again and again. And they are fundamental concepts. It is not just a formula application, they are fundamental concepts. So next is the definition of event. That's the main thing in probability. In theory of probability, this is the one. Definition of event. Excuse me. So what is an event? Now we say one particular occurrence. Now we are talking of event in terms of a random experiment. So event is a subset of a sample space S. This is the definition, very important definition. It's a subset of a sample space. Now, sometimes an event contains a single sample point. An event consisting of a single sample point S is called as an elementary or simple event. The events other than elementary events are called as mixed or compound events. Then we have set S is sure or certain event. That means the sample space S is a subset of itself and it is called as the sure event, and the empty set is called as the impossible event. So let's look into an example. Again, we'll take the example of rolling a die. When we roll a die, what is the sample space? You get these outcomes 1, 2, 3, 4, 5, 6. Now we say event is a subset of the sample space. So example of elementary events I'll give first. So E1 is the event that the number 1 occurs. It's an elementary event. E2 is that when I roll a die, element 4 occurs, let's say. So these are examples of elementary events. Now E3 is an event that number 5 occurs. So these are example of elementary events. Mixed events, it's an event, but E1, let's say the event is that 1 or 2 or 3 occurs. So how do we write this? We say E1 is the event that E1 is an event that a number less than 4 occurs. So this is not an elementary event. It is like more than one sample points come into the event. And this event is a subset of sample space. So what's the definition of an event? It's a subset of a sample space. Okay. Now, I want you all to answer. I will write an event. How will you define the event verbally? You please tell me. The experiment is that of rolling a die. So what is this event 2? Can anybody say? Don't feel shy.
Answer.
Yeah, it's a mixed event. Good. Yes, I got an answer on the chat. It's the event that a prime number occurs. That a prime number occurs. It's an event that a prime number occurs. All right. Tell me about this event. Okay. Good. 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 So E3 is the event that a multiple of 3 occurs. Or we can say a number divisible by 3 occurs. Look at this one.
Sir, getting a even number.
Good. So E4 is the event of getting an even number. Event that an even number occurs. So we see that even there are multiple events we can uh, define. We can say 1, 2, 3, 4, 5, which means even that a number less than 6 occurs, so on. So these are all events. Events are all subsets of sample space. Okay. Now, what is this event? What is this event? 1, 2, 3, 4, 5, 6. What is this event? Good. This event, very important, because when you roll a die, definitely this event will occur because it contains all the possible outcomes. This event is equal to the sample space. So this event E is called as the sure or certain event. Certain event. Okay. Next, suppose E is an empty set. And what is this event called? Good. So E is called as an impossible event because when you roll a die, it is not that none of these 6 numbers occurs. At least one of them should occur. All right. It is not that when the coin is tossed up, uh, you know, instead of heads and tails, the coin just falls and stands on its edge. It doesn't fall either heads or tails. It doesn't happen. Okay. We don't consider cases like that. Or we don't consider that when we roll a die in quicksand, you put the die and then the die disappears, or the die sinks into the mud, and those kinds of things we are not considering. The regular, when we roll a die, one of the events should happen. So a null set is an impossible event. So all are phi s so on, they are all number of all the subsets of S, all are subsets of S, and all are called events. So starting from impossible events to sure events. Now my question is, if question, that's an important note. If a sample space S has n sample points, then sample points or simple events, then the total number of possible events in such a random experiment is, what is the total number? N plus 1. No. Think. Let's see. Second answer has come. S power n, not S power n. 2 power n, close. 2 power n is close, but not accurate. Again, read the proposition carefully. Good. Correct answer. It is 2 power n minus 1. So here is the principle of counting. How do you count? So let us take example of, the sample space containing 6 points. So now the event, the how to count. One method of counting, the tedious method of counting is this. Suppose you don't use the concepts of permutation and combination. How do you count? So event, let e power s be set of all the events. Okay. So the first set of events will be those events that contain single points. There are 6. Then those which contain double points. 1, 2, 1, 3. Oh, there are so many. 1, 2, 1, 3, 1, 4, 1, 5. 1, 6. They are double points. Huh? That means you will choose to, here the count is, we will mark in different color, 6. Double points means you select any 2. So you get from 6, you select 2, 6C2. And then it can be, yeah, that's it, 6C2. It is not, it's a single roll of a die. So you get 6C2. 6C2, 6 into 5 by 1 into 2, so 15. Then you can have 3 events. 1, 2, 3, 1, 2, 4. Okay. 1, 5, 6. And then all the possible combinations of the events. So this is event, each subset, right? The number of subsets. So this is 6C3. 6C3 is 6 into 5 into 4 upon 1 into 2 into 3. So 2, 3, 6. So 6C3 is 20. Then you have 4 events. So on. So you get 6C4. Now 6C4 is same as 6C2. You get 15. Then you have 6C5, 1, 2, 3, 4, 5. You get 6 cases in this because one event is formed by omitting any one of the numbers. There are 6 numbers. You keep omitting. In one, you omit 6, other 5, other 4, other 3, 2, 1, so on. So you get 6C5, which is 6. And last, the sure event. the sure event. This is only possibility is one possibility. This is only one possibility. 6C6. So basically the total number of subsets of S is 6 plus 15 plus 20 plus 15 plus 6 plus 1. So you can count 30, 50, 62, 63. Now this is equal to 2 power 6 minus 1. 2 power 6 is 64 minus 1. So there are 6 points in the sample space. This is 64. So how do you calculate this 2 power n? How do you calculate this 2 power n minus 1? So this is by the permutation combination method. So now we have 1, 2, 3, 4, 5, and 6. This is our sample space. I want to form an event. Okay. Now I take up each element. I take 1. I have 2 options now. I can choose this one to be part of this E, or it may not be part of this E. So I have 2 options. Okay. This one can either be part or it may not be a part. So taking that one, so with one, I have 2 possibilities. Either to include one within the event or exclude the one within the event. Understood? Either I can include or exclude. So I have 2 possibilities. Next, I take the second event. Now, again, I have 2 options. I can include that within this event or I can exclude. So again, I have 2 possibilities. Now it is a sequence. I can include one, the first one and the second one. So it is a multiplication. So 2 into 2. Then I come to the third one. I have again 2 options. Either I can include this event within E or I can exclude it. So like that, for each of the sample points, I have 2 possibilities. So I get 2 power 6. All right. However, one possibility is that because I am either choosing or omitting the first one, choosing or omitting the second, choosing or omitting the third. Like that, when I see one possible case, one case will be such that I omit all of them. I omit all of them, but that's an impossible event. And what is the question? Total number of possible events in such a random experiment is. So total number of possible events. So there's one possibility that I completely omit all the sample points. So that becomes a null set and it's an impossible event that we do not want. So we get the total number of subsets of S or non-zero subsets of S is 2 power 6 minus 1. So the same logic is used if there are n sample points. So each of the sample point I can include or exclude within the event. So I have 2 possibilities. Multiplying that 2 into 2 into 2 into 2 n times, I get 2 power n, and one event will be such that I choose none of them. So that impossible event I have to exclude. So I get 2 power n minus 1. Okay, did you understand this? This is an important question. an important result. If you have understood this, okay, please say yes in the chat box to me. If no, then you say no. I will explain again. Only one yes, two yes, three, good, four. Quickly. 5, 6. All right. Okay. One more person has to answer. If you don't feel shy, if you didn't understand, I'll explain again. This is a very important topic, by the way. So again, see, it is like S is this event. I'm explaining again. S is the set of all points. Now, from this, any subset I have to make. The question is find the number of non-zero subsets of S, because any subset of S will be an event. So then we can say find the number of non-zero subsets of S, and that is same as find the number of events of the random experiment. So I have to find the subset. Now in a subset, I have two options. I take the first item, the first sample point. I can include this or I can exclude this. That means I can put it part of E or I can omit it. So there are two possibilities. So I get 2. Then multiply that 2 with the next one. The next one possibility, again, I have two possibilities. I can include that in E or not include that in E. So 2 possibilities. Third one, again, I can include or not include. Like that for all the N, I can include or not include. So I get 2 into 2 into 2 N times, so 2 power N. So in this particular case for a die, we get 2 power 6. Minus 1 is the case where completely none of them are included. That means we have chosen a set which is empty. That is an impossible event that we need to exclude. So we cannot include that within the count. So 2 power N minus 1 is the size of the sample space. The number of subsets of the sample space which form events. So this is a very important definition, because whole thing in probability is if you can identify the event correctly, you will get the probability calculations correctly. Now, yeah, there are 3 important definitions before we go to independent. So the first one is called as equally likely events. So there is no bias between the events. It is each of the event has equal chance of occurring. So the events of a sample space are said to be equally likely if none of them is expected to occur in preference to the other. So when I roll a die, 1, 2, 3, 4, 5, 6, all the 6 numbers have the same likelihood of occurring. It is not that, okay, 2 will occur more number of times than the other numbers. If that is so, then 2 is, it's a bias die. There is a bias in the die. For an unbiased die, when you roll, all the events occurring of 1 or occurring of 2 or occurring of 3, occurring of 4, occurring of 5, occurring of 6, they have equal chances to occur. Such events are called as equally likely events. Now, these events are not restricted to simple sample points. It can be, the events can be complex also, in the sense it can be mixed events. So it is like their occurrence is, it is not that one has a preference over the other. For example, let us see this example. Rolling of 2 dice. Now these are the events. Now, what is the likelihood of 2 2 occurring and 4 6 occurring? They're equally likely. You cannot say that, okay, one will occur more than the others. So these are called as equally likely events. Okay. Now I can give another example. E1 in rolling a die, E1 is the event of getting an odd number, and E2 is an event of getting a even number upon rolling a die. Okay, this is on rolling a die. So here E1 and E2 are equally likely. They're equally likely because there's a same when you roll a die, there's an equal chance of either odd number occurring or even number occurring. However, the events may not be equally likely. So equally likely means the probability should be same. So the count, the subset should be having the same size. If the subset is not having the same size, then they're not equally likely events. Okay. For example, this is example 1. Another example of equally likely events is 1 2 sorry, not 1 2 2 3 5 1 4 6. Again, these are equally likely events. However, example 3, if I choose the event 1 2 4 5 and another event 3 6, so this is a number divisible by 3 and this one is a number not divisible by 3. Now when we roll a die, there are 4 events 1 2 3 4 favoring the 4 sub events, the favoring the occurring of event E1. That means the chances of E1 occurring is greater than the chances of E2 because there are only 2 possibilities. Here there are 4 possibilities. So these are not equally likely events. It is an unbiased die. but these are not equally likely events. Interesting. If it's a biased die, okay, some particular number occurs more frequently than the others. But it is an unbiased die, but you can get an, it need not be equally likely events. Okay. These are very fundamental concepts of events, what I'm saying, to understand. So equally likely has to do with the number of possible. I am rolling the die once. And what is the possibility? So for two events, there has to be an equal chance to occur. But here we see that E1 has greater possibility of occurring than E2. So these two, E1 and E2, cannot be equally likely. Clear? Is that clear to everyone? Okay. Just if you have doubts, raise hands. I'll ask, I'll give examples. I want you all to answer. Okay, whether the event is equally likely or not. So I'll take experiment of tossing two coins. Experiment of tossing two coins. So sample space is 4. This is easy. Experiment of tossing two coins. So first part. E1 is the event of E1 is the event of identical outcomes on the two coins. Identical outcomes on the two coins. E2 is the event of distinct outcomes on the two coins. Tell me whether E1 and E2 are equally likely.
Yes, sir. Equally likely, sir.
Very good. Who said that?
Sir Ashutosh.
Yeah, good. So why they are equally likely? What is E1? What is E1? Identical outcomes means you have HH and TT. So both coins have identical outcomes. So first coin has heads, second coin has heads. Or first coin has tails, second coin has tails. So this is E1. What is E2? The event of distinct outcomes on the two die. So you get HT, TH. Okay. So, but the count of the occurrences is 2 and 2 here. So they are equally likely. So E1 and E2 are equally likely. Now I'll give another example. A is the event that at least one tail occurs. B is the event that no tails occur. Tell me whether A and B are equally likely events.
Not equally likely.
Hmm. Why? Identify the events. Identify what is A.
Sir, head tail, tail head.
Head tail, tail head,
Tail tail.
and
Tail
tail
tail.
tail. Correct. So at least one tail occurs. So one tail on the second coin, or one tail on the first coin, or both tails on the both coins. So these are the possibilities. Now B is the event that no tail occurs. So only possibilities heads. So the experiment is of tossing two coins. So this is the outcome. So this has greater chance of occurring than this one. So A and B are not equally likely events. So it is not about just biased coin or a biased die for it to be equally likely. It depends on how we define the event. The whole exercise is how we define the event. In a problem, we should understand what is the event. Once we are able to do that, we are through. We will be able to solve the problem. The main question student faces difficulties, he doesn't understand the event properly. If the event is understood, probability problem is solved. If we know the sample space and if you know the event, probability is done. You get it. Now, mutually exclusive events. Exclusive. Mutually exclusive means when one occurs, the other event cannot occur. The other event will not be able to occur. Exclusive. So a set of events is said to be mutually exclusive if occurrence of one of them rules out the occurrence of any of the remaining events. Okay. For example, simple, when we toss a coin, if head falls, then occurrence of tails is not possible. If tail appears, then occurrence of heads is not possible. So they are mutually exclusive. Either heads will fall or tails will fall. Both cannot happen simultaneously. Okay. Similarly, when we roll a die, so 1 or 2 or 3 or 4 or 5 or 6, they occur. Now, if one of the number appears, none of the other numbers can appear. So occurrence of one excludes the possibility of others occurring. So such events are called as mutually exclusive. But now I'll give examples of compound events. So simple events is easy to understand. Now I'll give an example of compound events. Let us say this. Examples on mutually exclusive events and those that are not. So examples of those events that are mutually exclusive and those that are not. So experiment is rolling of a die. The experiment is rolling of a single die. Okay. Now, so E1 and E2 are two events. Now we talk about whether they are exclusive. So 1, 3, 5 and 2, 4, 6. So 1, 3, 5 are odd numbers. 2, 4, 6 are even numbers. So if an odd number occurs, even number cannot occur. So see, E is the event of an odd number occurring. E2 is the event of an even number occurring. Now these two are mutually exclusive. Okay. These two are mutually exclusive because when one occurs, other cannot occur. Okay. Now if we see, now next, I'll come to another definition. Look at this 2, 3, 5 are the basic prime. One is not considered a prime because it's a common factor to all. So let's take this example. So E1 is the event of prime number occurring. Of a prime number occurring. Then E2 is the event that other than prime number occurs. So here we can see that E1 and E2 are mutually exclusive. If one occurs, other cannot occur. Okay, let's take another example now. It's slight twist. So E1 is the event of a prime number occurring. E2 is the event of an even number occurring. So E1 is the event that a prime number occurs, or E2 is the event that an even number occurs. Now, are they mutually exclusive? What is E1? 2, 3, 5. What is E2? Second event, even number occurring. 2, 4, 6. So one event does not exclude the other event to occur, because suppose the number 2 falls. When you roll a die, you get the number 2. Then even has occurred. And also you can say E2 has also occurred. E1 has occurred because 2 is a prime number. And E2 has occurred because 2 is an even number. So you get an issue here where if a number occurs, that outcome belongs to more than one event. Then they are not mutually exclusive. E1 and E2 are not mutually exclusive because E1 intersection E2 is a non-zero set. You get some set. So very important. If two events are mutually exclusive, then that those intersection of these two events should be fine, null set. Okay. Second extension of this, if E1, E2, E3, En are n events which are mutually exclusive, then E1 intersection E2 intersection E3 intersection En, or all the intersection is fine. That means no subset belongs commonly to any two events, like that. So this is about mutually exclusive. These are very important definitions. Equally likely, mutually exclusive, and then we have exhaustive events. Exhaustive events means if the events occur, they cover the entire sample space. So set of outcomes or events is said to be mutually exhaustive if it covers each and every possible outcome of the sample space of an experiment. That is, at least one of them has to occur in the performance of the experiment. So if the sets of the events E1, E2, so on up to En are exhaustive events, then their union will be equal to the sample space. So example here, this E1 here, the first example, E1 and E2, occurrence of odd number, occurrence of even number. Together, they cover the entire sample space. So they are exhaustive events. Together, E1 and E2 cover the entire sample space. Then E1 and E2 here, one is prime and other is non-prime. These two again combine to give the entire sample space. So they are exhaustive events. Again, this one, 1, 2, 4, 5, and 3, 6. Together, they form the entire sample space. So they are exhaustive events. Now let us take example that which is not exhaustive. This one. E is the event of a prime number occurring. E2 is the event of an even number occurring. So 2, 3, 5, 2, 4, 6. So you get 2, 3, 4, 5, 6, but 1 is missing. So this E1 and E2 together, they give us 2, 3, 4, 5, 6, but 1 is missing. So this cannot be an exhaustive set of events. So the last one in the definition, this is a very important definition, which compound probability and Bayes theorem, these are all based on this definition. Very important basic probability theory. So independent events. Two events are said to be independent if occurrence of one of them does not depend on the occurrence of the other. The other one may occur, may not occur, but this one is not dependent on whether that will occur or not occur. All right. Simple example. Tomorrow it may rain. Tomorrow, E1 is the event that it rains tomorrow. Okay. E2 is the event that um, you eat an ice cream tomorrow. Of course, ice cream is related because it may cause cold. So there is some dependence on that. Let us say uh, E2 is the event that uh, you eat your lunch tomorrow, the general lunch. Now, whether it rains or does not rain, you will eat your lunch. Okay. Eating of the lunch is not dependent on whether it rains or not. So then those two events are independent. If there is some dependency, that only if this event occurs, the next one can occur, then they are dependent events. So that is, so note there is a clear difference between mutually exclusive events and independent events. So let us take this example. Two fair dice are thrown. E1 is the event of first die showing an even number. E2 is the event of second die showing an odd number. So when I roll a die, E1 is the event that the first die gives me an even number. E2 is the event that the second die gives me an odd number. Now these two will be independent events because the result of first die does not affect or depend on the second die. It does not depend on the second die. Your second die may get an even number or odd number. The first one does not depend. So it is an independent event. Okay. All right. But of course, these are not mutually exclusive events because both the events may simultaneously occur. E1 is the event that the even number occurs on the first die, and E2 is the event that odd numbers occurs on the second die. So both can happen simultaneously. The way we have defined event is different in this case. So it depends on our definition of event. So these are independent. But example 2, again, two fair dice are thrown, but even is the event of getting the sum on them as an even number. In the first case, the event 1 was event of first die showing an even number. No, now both the die are involved. The sum of the outcomes of die 1 and die 2 should be even. And E2 is the event of getting the sum of them as odd. So the sum either can be even or odd. Both cannot occur simultaneously. So these are not independent events. They are actually mutually exclusive events because if one occurs, other cannot occur. So independent and mutually exclusive cannot go together. If two events are mutually exclusive, they cannot be independent. And if they are independent, they cannot be mutually exclusive because any one of them can occur. Intense, huh? So the concept of events, this has to be grounded very deeply. And that's why I've spent a lot of time on events. And I think it will help if you have not understood, it will help to hear the recording of this again and again. It's a very important. You just have to get this right. And then we will do problems on probability. Now we'll go a little fast with the probability theory. So now there's the concept of probability. And there are multi definitions of probability. So let us visit one by one. This is called as the classical definition. The first definition of probability is the classical definition of probability. So this is also known as the mathematical definition or a priori definition. And most of our problems are on this, but questions are asked on the basic concept of either classical definition or the next one. There are three: classical definition, axiomatic definition, and statistical definition. So we will cover one by one. So classical definition of probability. So in a random experiment, let there be n mutually exclusive, equally likely elementary events, which are exhaustive as well. So there are n mutually exclusive. That means the total sample space. There is n mutually exclusive events, equally likely elementary events, which are exhaustive as well. That means we are considering the entire sample space, and n is the size of the sample space. Okay. So here you see in this particular definition, the concept of sets is not introduced at all. So in a random experiment, let there be n mutually exclusive, equally likely elementary events, which are exhaustive as well. Now let E be an event of the experiment. If m elementary events form E, or in other words, m elementary events are favorable to E, then the probability of E is defined as probability of E is m upon n. Number of elementary events in E divided by the total number of elementary events in the random experiment. So this is called as a classical definition or a priori definition, because you can guess the outcomes beforehand. A priori. A priori is a French word, and beforehand, you know it. So example, find the probability. A die is rolled. 6-faced die is rolled. What is the probability what is the probability that a number occurs which is either divisible by 2 or by 3? Okay, I want answers. Please attempt, then I'll explain. I got one answer so far. Let me see others. Please give the answer. A number which is either divisible by 3 or divisible by 2. Okay. So sample space S is 1, 2, 3, 4, 5, 6. Therefore, N is total number of elementary events. This is equal to 6. Now, E is the event that a number is either divisible by 2 or 3. 1 is not in that category. 2 and 3 are in that category. 2 is divisible by 2 and 3 is divisible by 3. So one of them at least should be Meaning it should be divisible by at least one of two or three. Now 4 is divisible by 2. 5 is not divisible either by 2 or 3, so it is omitted. 6 is divisible both by 2 and 3. So we get this. So M is number of elementary events favorable, number of elementary events favorable to occurrence of E. So therefore, probability of this event E, we write like this. We say it is M upon N. This M is equal to 4 and N is equal to 6. So you get 4 by 6 or 2 upon 3. So it's all about writing the event properly. So this is the classical definition. So number of elementary events favorable to a particular event divided by the total number of events, simple events, elementary events in the sample space. This is the definition of probability. So this is the probability that this can occur. Now let's look at some basic important concepts. Now look at the basic corollaries to this definition. So if E is an event, then E dash or E bar denotes the event E not occurring. Event E not occurring. Then the number of elementary events, in E bar is total number of events minus M. Okay. Total number of events minus M, those are favoring to event E to occur. Therefore, probability of non-occurrence of E is P of E bar, which is N minus M by N. You divide this by N, you will get 1 minus M by N, which is 1 minus PE. So here comes the important result. Probability of an event occurring plus a probability of the event not occurring is equal to 1. Okay. So E is also called probability of success, P of E, and P of E bar is also called as probability of failure. Sum of these two probabilities is 1. Also, since M will be less than N and M has to be greater than or equal to 0. So M value, because number of events favoring a number of elementary events favoring an event, that has to be less than or equal to the total number of elementary events. So M lies between 0 and N. Divide by N. We get 0 divided by M by N less than or equal to 1. So which gives that probability always lies between 0 and 1. 0 probability means it is an impossible event. 1 probability means it's a sure event. And P of E bar, because P of E bar is 1 minus P of E. So if P of E lies between 0 and 1, P of E bar must also lie between 0 and 1. So again, probability of certain event is 1, probability of impossible event is 0. Okay, then this is odds in favor, odds against. Odds in favor, odds against, that terminology at our level we don't use, but that sometimes if in general ability you are asked a question, you should know this. So if E is an event of a sample space, then odds in favor of E is probability of E is to probability of E bar. That means odds in favor. What are the number of favorable events versus or to the ratio number of unfavorable events. Okay, so that is the way it is counted. All right, let us see. This is a mistake here. Next, odds against E is defined as P of E bar is to P of E. So here is an example. If odds in favor of E are A is to B, all right, then probability of E is A by A plus B. And probability of E bar is B by B plus A plus B. So how does this happen is because the number of events favorable to E is A. Okay. So P of E is proportional to A, you can say, and P of E bar is proportional to B. Okay. Because in fact, the number of events, now if total number of events are A plus B, suppose they are not A plus B, they have to be A plus B because A plus B should P of, so here you get P of E plus P of E bar should be equal to 1. Okay. So let's say proportionality constant for both of them is K. There has to be a same proportionality constant. So you get K as 1 by AB. So P of E is AK, P of E bar is BK. Then, so P of E you will get as A upon A plus B, and P of E bar we get as B upon A plus B. So odds in favor and odds against. So odds in favor means P of E is to P of E bar is odds in favor of the event E, and P of E bar is to P of E is odds against. Now what is the problem with classical definition? Mostly we use for our practical purposes classical definitions, but sometimes this classical definition of probability fails. So it fails to apply when the outcomes of the trial are not equally likely. If they are not equally likely, this completely fails. Our definition, calculation of probability fails. Suppose a die is biased, and let's say numbers 1, 2, 3. The die is biased to this. So more times 1, 2, 3 can occur than 4, 5, 6. Then the events are not equally likely. So if you say probability of number 2 occurring is 1, 1 by 6, it may not be so. It may be 3 by 6. Half of the times 2 occurs. So this definition fails when the outcomes of the trial are not equally likely. And it also fails when the number of outcomes of the experiment are infinite, because it is totally dependent on n. So if the event belongs to a continuous domain, continuous set of events, the continuous sample space. If your sample space is continuous, then gone. We'll not be able to evaluate by this definition. And the enumeration of all the equally likely events is not possible. That means if it's a continuous sample space, again, we'll not be able to count what is n. So in these cases, this definition fails. This classical definition. The second part is statistical definition, that is easier. First part is the easiest. The second part, it is not difficult. Third part is the axiomatic. These are the basic, and then we begin with the probability problems, simple ones. I'll do at least 4 or 5 today. So this is called as the frequency definition. Statistical definition is also called as the frequency definition or empirical definition. That means based on experiment, or a posteriori definition. That means to be able to predict the probability of an event, I should have studied the past events. For example, a biased die is there. So I roll the die 10 times and I count the number of times the number 2 occurs. Suppose 2 occurs 4 times. In 10 throws, 2 occurs 4 times. Yeah. Just a second. In 10 rolls of the die, 2 occurs 4 times. There's some issue. Okay. Some issue. Something is happening. Just a second. I'll just close and open. Mhm. Okay. I'll just explain. There's some disconnection. Yeah. Suppose in 10 rolls, you get probability of number 2 occurring 4 times. That means 4 times it has occurred. So you say the probability of that occurring is 0.4. But suppose you roll that die 100 times. And let's say 2 appeared, say 35 times. Then we say the probability is 0.35. That means it is based on our previous performance of the experiment. That is a posteriori definition. So let a random experiment be repeated n times and let an event be observed as an outcome m times. Then R of E is m upon n, is defined as the relative frequency of the event E. So the experiment is repeated n times and the event is observed as an outcome m times. So m by b is the relative frequency. Then the probability P of E of the event E is the limit of this relative frequency as the number of repetitions n is increased indefinitely. So P of E is defined as probability of E is limit n tends to infinity of the relative frequency, that is m upon n. So this is statistical definition. It has got great practical use. Okay. In the sense, like an industry, suppose in a manufacturing of the car or manufacturing of any industrial component, you know, batch of 50,000 is manufactured at one go. Suppose a batch of 50,000 is manufactured at one go. Of the 50,000, let's say 200 get defective in whatever is the definition, whatever is the defect. Let's say 200 times the piece comes out defective out of 50,000. So then you say 200 over 50,000 is the probability of getting a defective piece. But then what if I increase the batch size to 1 lakh? So 1 lakh, products are at one go, they are manufactured through the machinery, whatever the process they're using. Now, if we get 400, then the probability is equal, but we may not get 400. So it all depends on this N. So in an industry kind of a setup where you have to predict for the next and reduce the probability of errors, it is based on your previous experience. So statistical definition of probability, although is of great practical use in science and engineering, is not conducive for mathematical approach, as the number N cannot be clearly defined. Should I take 50,000 or should I take 5,000 or should I take 1 lakh? It is not clear. So that is the limitation of statistical definition. However, it is used. It is not out of place. It is used. Next is the axiomatic definition, and this is what we use maximally. The definition 1 and definition 3 are combined, and that is what we use. Okay. Now, axiomatic definition of probability, it uses set theory. Now, let us define the finite sample space. Now, probability is defined as a function. So, probability function is defined as, so it's a function between power set of R. What is a power set of S? Power set of S into R. Power set of S means set of all the subsets. So SP, power set is set of all the subsets. That means all the possible events. And there are numbers, real numbers between 0 and 1 here. So no matter what the event is, the events are mapped to some values between 0 and 1. Okay. So then we say that this is a probability function. So we are defining a probability function. The domain is the power set of S. Power set of S, that is set of all the subsets of S, and map into R. That is okay as long as these three axioms are satisfied. If these three axioms are not satisfied, then you cannot define this probability function. First, axiom of positivity. Probability of E is greater than 0 for every subset of S, greater than or equal to 0. Axiom of certainty. Probability of the sample space should be 1. That means the minimum value of probability is 0, maximum value is 1. That is what we have described here by these two axioms. And third one, axiom of union. If E1 and E2 are mutually exclusive and disjoint subsets of S, then P of E1 union E2 is P of E1 plus P of E2. So this is what is the, if these three things occur, then we say we call this as a probability function. And how we define probability of an event in this case? Now it is the cardinal number of the event E by the cardinal number of the event S. Cardinal number is the size of the set. Cardinal number of E is the number of events of the number of sub events of E. S is the sample space. So number of events of the sample space. So it is same as M upon N. So this is the axiomatic definition. Okay. Now, sometimes questions come on the kind of definitions and probability. They are just to check your concept. They don't ask much, but they just check the concept. So now I'll give you a few problems. Simple ones. On basic definition of probability. So one ticket is drawn at random from a bag containing 30 tickets. Numbered 1 to 30. Find the probability of getting a prime numbered ticket. Find the probability of getting a prime numbered ticket. Chalo, let me see the answers. I want to see the answers in the chat. Okay. So many of you have answered. Good. So S is 30 tickets. So N of S is 30, the size, or this is also N, the total number of events of the elementary events of the sample space. So N of S is 30. E 2, 3, 5, 7 between 1 to 10. Then 11, 13, 15 is not, 17, 19. Then 21 is not, 23. 25 is not, 27 is not, 29. So 2, 3, 5, 7, 11, 13, 17, 19, 23, 29. How many of them? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. So their N of E is 10. Therefore, probability of this event is 10 upon 30, which is 1 upon 3. Okay. Next, probability of dice. So this everyone did. 2 dice, 6 face dice are rolled simultaneously. Find the probability uh, of, find the probability of, let's say, find the probability of the sum of the numbers is 6. Do this. The difference of the numbers is 2. The sum of the numbers is less than 10, less than 11. Okay, these three. Okay, some answers I've got. Good. 2 correct answers so far. So S, when 2 dice are rolled, you get 6 into 6, 36 options. First die can have 6 and the second die can have 6, any of the 6. So we get 36 options. Now E is the event that the sum of the number is 6. So you can get, on first you can get 1 and 5 on the second. You can get 2 and 4 on this on the second, then 3 and 3, then 4 and 2, and 5 and 1. So n of E, the cardinal number of this set, 1, 2, 3, 4, 5. So probability, the first case, the probability of E is n of E by n of S. So it is 5 upon 36. Okay. Now second case, S is the same. N of S is 36. E, the difference between the two numbers should be 2. The difference of the numbers is 2. So we can get, start with 1, then you can get 3. If you have 2, then you can get 4. And if you have 3, you can get either 1 or 5. So 1 is already there. So I'll write 5. And if you have 4, you'll get 6. Now, this is on the first die. This is on the second. First die, second, first die, second, first die, second. You can reverse it. It can be just the opposite. 1, 3, 3, 1, 2, 4, 4, 2, 3, 5, 5, 3, 4, 6, 64. So n of E is 8. So 1, 2, 3, 4, 5, 6, 7, 8. So probability of E is n of E upon n of S. So 8 by 36. So 2 upon 9. That's the answer. Second one. The last one is E is event that sum of numbers is less than 11. No, less than 11, there can be some basic sum. When two dice are rolled, the least sum is 1 plus 1, 2. So then you have 2, 3, 4, 5, 6, 7, 8, 9, 10. Instead of doing that, I will choose the negation, the complementary event. The complementary event E bar is the event that the sum of the numbers is 11 or greater than 11. Here it is less than 11. So it should be 11 or greater than 11. Now E bar, the only possibility so of 11 is you get 5, 6. First you have 5, on second you have 6, or 6 on the first, 5 on the second, and then 6 and 6 on both. So probability of E bar is n of E bar by n of S, which is 3 upon 36. So probability of E will be 1 minus probability of E bar. So 1 minus 3 upon 36, which is 33 upon 36, which is 11 upon 12. Okay. So some of you have got correct answers for all of this. So probability problems are interesting. They are simple and verbally appealing. We can do it easily. I will give you an exercise to do. Okay, I'll try to upload it by today evening itself. So next question, I'll give you last question for today. Five coins are marked with 2 and 3 on either side. So it is not heads and tails. It is 2 or 3. These are thrown, these are tossed simultaneously. What is the chance of obtaining the sum as 12? Please attempt. Good. One correct answer. Others? Size of the sample space. This is very important to count. Size of the sample space. Now the sample space, the total number of, see, either there is 2 or 3. So 5 coins are tossed together. So 5 coins are tossed together. Now each of the event can be like either 2 can be reflected or 3 can be reflected. How to count this N of S? The first position, so there are 5 coins. We'll mark like this. So this is one particular outcome. 5 coins are tossed. Now the first coin can get either a 2 or a 3. Either 2 or 3. So there are 2 options, 2 possibilities. Simultaneously, the second can get either 2 or 3. So again, 2 possibilities. The third will get either 2 or 3. The fourth will get either 2 or 3. And fifth will also get 2 or 3. And because it is and, first coin can get 2 or 3, and second will get 2 or 3, and third will get 2 or 3. So by multiplication principle, 2 power 6. Some of you in your answer, what you have done is you have done 2 power 5 minus 1. The mistake is here, it is not that we are finding the subsets of S. In subsets of S, there will be a case when none of the event occurs. So that we subtract. So don't use that formula blindly here. Here, each of the events, each of the coins, one of the number will occur. So either 2 or 3. So you get all the possibilities is 32. 32. So now what is the event favorable to E? This is interesting. Now we have to count. See, if all 2's are there, 2, 2, 2, 2, 2, we get 10. Sum as 10. If all 3's are there, we get 15. Now 12 is in between. That means try to replace 1, 2 by 3 and see. So if you replace 1, 2 by 3, you get 8 plus 3, 11. You don't get 12. So replace 2 2's by 3's. So 2, 2, 2, 3, 3. Now the sum will be 6 plus 6, 12. Yes. Now you cannot do 3 3's and 2 2's. So this is the combination. You have to get 3 2's, 3 2's and 2 3's. Now in which order you will get? Now here you have to use the concept of permutation. So which order? So if you remember I want to arrange 3 2's and 2 3's. Okay, randomly. Number of possible ways. are 1, 2, 3, 4, 5, 5 factorial upon 3 factorial, 2 factorial. Alike, there are 3 alike of one kind and 2 alike of another kind. So we get this. So 5 into 4 into 3 factorial by 3 factorial into 2, 3 factorial cancels. So 5 into 2, 10. So the answer is probability of this event occurring is 10 upon 32, which is 5 upon 16. So 10 upon 32 is 5 upon 16. So here is the catch. To count, you have to use the concept of permutations. Okay. So if you are not good at permutations, so you will require a lot in general ability and also in this. The questions directly on mathematics, engineering mathematics, are more concept oriented in probability, but there has to be some understanding of calculations using permutation combination. But there is a section, general ability section, in that permutation combination is a unit. So you will be asked questions from permutation combination. So you should briefly go through, and I will also, for general ability, I'll be covering that. I think it's better I cover now, and then parallelly with probability, it will be useful for you. Okay, I'll end the class here. I will try to upload this as soon as possible. Yesterday's class and today's class on Moodle Cloud, not Moodle Cloud, aoc.akshayclasses.com. So from there on the Moodle platform, you can see the, I'll try to give questions also. I'll upload the questions. Thank you. I'll end the class for today.
Thank you, sir.
If anybody has any doubts, you can wait, others can leave.